like to first thank everyone for joining us today. I think it's been a great morning. We had a lot of informative presentations that covered a broad range of technologies, many that we don't hear about in some of the regular communications about AM, which I think is great. Those presentations primarily came from development council partners, and we also had a lot of great questions from attendees. As Sean mentioned this morning, I was recently appointed head of product here at Dyndrite, and this is after several years of additive manufacturing experience in aerospace. This was as director of additive manufacturing at Blue Origin. In this role, I had the opportunity to live many of the challenges faced by the industry today and actually meet many of you presenting or joining in attendance over the next couple of days, which I think is very exciting. Prior to this role in AM, I was leading in-space propulsion at Blue for a few years, where we actually developed components for AM. And before that, I was actually doing some of the component design, test, and operations for our engines and vehicles. Over the last few years, you may have actually had the opportunity to hear me argue, similar to what we heard from Nile at ANSYS this morning, about how geometry and toolpath relates to material properties and how they further relate to some of the qualification strategies that we are using in the industry today. And this is really an area that I'm very passionate about, and one of the primary reasons I'm with Dyndrite. We are speeding up, automating, and enabling new opportunities for machine and process development with the goal of reducing the qualification burden on our end users. And I'd like to follow up on Harshal's introduction to the tool this morning. We have developed a new geometry kernel to address the large amount of information, data manipulation, and workflow solutions that we anticipate as the industry evolves. And this kernel affords us the speed and robustness to even hold the conversation about advanced toolpaths. So for this, I'm super excited about the panelist discussion we're having. I'd like to start by introducing them and then have them give a brief bio for themselves. So I'd like to first bring on Kevin from Renishaw.
Hello, everybody. How's it going?
So Kevin, I do not know if everyone was able to attend your talk from earlier today. So if you could give a brief bio, that would be great.
Absolutely. So yes, my name's Kevin Brigden. I'm an applications engineer with Renishaw in the United States, Illinois. I've been with Renishaw since 2014, originally coming from a background in motorsports engineering. One of the things that I love about additive, in particular at Renishaw, is the fact that I get to deal with so many industries and different types of businesses, and to work with people to develop designs for additive manufacture that aren't just about the print process. It's also about the how you're going to inspect and how you're going to finish machine these components too.
Hey, thank you, Kevin. Next, I'd like to bring on David with Aurora Labs.
Hello, everybody.
We can hear you, David.
Okay, great. So maybe I'll jump on. Nice to meet everybody, even if it's only over Zoom. It seems to be the new way of things these days. So for those who don't know me, my background, I'm the founder of Aurora Labs. We're a company specializing in very high-speed printing processes, and we've developed some very interesting technology around that. And we're bringing our first range of ultra-high-speed products to the market at the moment.
Hey, thank you. Can we next bring on Yves?
Hey, everybody. It's a pleasure being here. For those who don't know me, my name is Yves Hagedorn. I'm co-founder and heading Econity 3D. We have specialized basically on building customized systems for 3D printing of metals. And as such, we are constantly striving with our customers and with our partners to find new innovations and to push the limits basically of this whole process with the final goal, of course, of industrial application on high volume. Great pleasure being here.
Thank you. I think we may be having some technical challenges with, with Andreas. So I think we'll be moving on to Barry.
Okay. Oh, we've got Len here.
Okay, I guess we can go with Len next. Len, please give us a brief introduction.
Okay, I gave a little bit of an introduction a few minutes ago in the talk, so I'll keep it brief here. My name is Len Wanger. I'm the Chief Technology Manager for Impossible Objects. We make industrial printers for end-use part manufacturing out of composite parts, fiberglass and carbon fiber. I've been in and around the graphics and CAD industry for a long time, and in the additive space since about 1991. Joined Impossible Objects officially in 2017, but I've been working with the company for several years before that in its embryonic stages.
Okay, thank you. And Will.
Morning, folks. Yeah, I'm Will Shabley. I've been in 3D printing since around 1999, and I have been basically helping people to either bring 3D printing technology and additive technologies into the foundry market for the last 10 years, and I do a little bit of proprietary additive development as well.
Okay, thank you, Will. So it seems like we are having some challenges with Barry and Andreas at the moment, so hopefully they'll be able to join us as the talk continues.
No worries. They will not be joining us. Go ahead, Steve.
Okay, thank you. All right, so as we've talked about, many of us are joining this conference remotely for the first time, full-time working from home. We're experiencing some technical challenges. I'm here in my garage. Similar to Ryan this morning, I do confess that I have pants on. And Ryan also mentioned that we are building an infrastructure in AM that needs fewer centralized resources than traditional manufacturing. In many cases, we may even be able to produce consumer goods in our own homes where we are today. I think this discussion will further enable this transition to fewer resources and further automate the resources that we do have. I'm excited about this panel because there's a lot of unique perspective with different manufacturing technologies, workflow, and processing, downstream processing steps for each of them. So we'll get started with a brief intro of the product team here at at Dyndrite, excuse me, prior team. And that product team actually has a lot of experience. I most recently joined from Blue Origin. We have experience from Boeing in other aerospace and in other existing CAD solutions within the industry, and also some service bureau type experience. So this interdisciplinary team has product design, mathematics, aerospace, and medical manufacturing backgrounds. And we're currently working with many industry partners, including experts on this panel today, to capture both the well-formulated problems that we have and also to try to tease out and understand some of the challenges that we really are barely scratching the surface on. So I'm going to give an overview of the Dyndrite Toolpath API and also the additive manufacturing toolkit. The toolkit actually is able to import and operate with native CAD files in addition to the traditional STL workflow. We position, modify, support, and then slice the geometry. This can be done with polygon contours, spline contours, or voxel contours. And the Toolpath workflow takes these operations much further, following the precedent of current Toolpath solutions, but also with a Python API to combine and automate the concepts that we show on the screen, such as zoning the parts, translating the parts, offsetting, doing large slice level operations, macro hatching operations, micro hatching operations, and then additional parameter formatting. For both the vector-based workflows that I show on the top slide or the top workflow and the raster-based workflow shown below, we're working with customers, many of whom are on this call today, to expose additional geometry and machine control and those attributes necessary for feature-dependent image and toolpath generation. So there are several obvious challenges that we have with Toolpath today? For one, it's slow. Slicing and hatching of large and complex parts can take dozens of hours to days in some cases. Currently, hatches are generally straight lines. This results in discontinuities in the toolpath with jumps, either slowing down the process or increasing component wear. Toolpath today only considers really the individual slices. We don't consider information or in the geometry far away from the slice we're actually interrogating for Toolpath. We have extensive data entry. New features and support strategies generally require lots of DOEs. This is generally done with external tools and then manually entered back into the build preparation software. There's currently a lot of proprietary information in the industry. These strategies are often considered proprietary for good reason, as they work with very unique machine configurations, and our software can be used to help OEMs develop some plugins for use with their machines. But also today, there are generally few tools suitable for the operations that we're talking about in a robust manner for these large data sets. So, kind of mentioned that we have developed a preliminary workflow to support many of the processes found in the industry. But we're looking forward to getting additional feedback from our panel here, and I'd like them to describe how they are doing Toolpath now and what challenges they're facing. I think I'd like to start with Kevin. How much has the Toolpath generation software changed in the last 10 years, and what do you see as the highlights?
I think you could answer this in one of two ways, depending on your level of optimism and pessimism. You could say that it hasn't changed significantly for the reasons you've just outlined. So the idea that you're taking what is effectively a 2.5D printing process of 2D layers, obviously, and we're still very much working with straight lines and points to points. But if I was looking at it more on the optimistic side, I think one of the real boons at the moment is increased integration with CAD. So CAD packages out there that are incorporating existing slicing strategies within their existing architecture, and really trying to cut down the number of instances of stepping out of the product lifecycle management cycle. That's one of the key areas in a lot of the more heavily regulated industries that has been important to work on. So for me, that's probably the single greatest advance in the last 5-10 years.
Okay, thank you. I guess, Will, you might have a different perspective on that. Oh, you're muted actually, so let me, oh, there we are.
Yeah, so I've been looking forward to the ability to handle bigger and bigger files as we've gone from 1999 printing at 300 DPI or lower up to goals of well over 600 DPI on much larger scale platforms. Being able to handle that data and look at the data in 3D without being pinned to one manufacturer's software, I think that opens a lot of doors for the whole industry.
Yes, I agree. I see Eve nodding there.
Thanks for activating my audio. Yeah, well, of course, I have to agree with Kevin. You could agree that not too much has happened, but on the other hand, yeah, also what we've just heard, that you can process a lot more data since 1999. So you could argue, well, we are still all using STL and we need to get away from all the STL tessellation, more into CAD. And into that direction, I believe a lot has changed. Also on the possibilities of simulation, which allow you, at least for laser-based 3D printing of metals, which allows you to sort of get a feeling on how much will the delamination be within your process, and that can give you a good idea on which parameters to use or not to use. So I believe it's a two-sided sword. A lot has changed, but there is maybe still a lot more to come, which will truly enable the industry for additive production.
Makes sense. So Len, what do you see as the largest challenge for you when you're creating Toolpath today? Your machine is very different than some of the other processes considered here?
Yeah, we have first of all, it's a very different system. It's an image-based system opposed to a G-code system here. I'd reiterate, we deal with a lot of the same issues that everyone else has mentioned, and we're trying to make a better user experience, make it directly to CAD. I'd say there are a couple unique things that I'd say we're looking at. One is we're trying to make an adaptive system that has a feedback loop to the operation of the machine, where you can feed the tool path back into the operating parameters. And with that, one of the key things is connecting it to a physical model or mathematical model of what's going on in the process. So actually make the tool path generation connected to simulation models and make that a dynamic feedback loop in real time. The other thing is connecting your toolpath generation to the full process there, including post-processing. And so that it's really about getting the final item out and making sure your toolpath can deal with things such as cleaning and surface finish.
Sure. So are you, Len, as a follow-up, are you able to actually execute much of that feedback loop today, or is that something that you're just prototyping, or how do you see that, or when do you see that becoming part of your production process?
Well, I'd say we're taking baby steps in it right now, where we're able to do inspection of layers that are coming out and adjust for them by changing process parameters. It's really just beginning. We need to get more sensors and better modeling of it. So we'll do that over time. The other thing that we do for toolpath generation, which is a little bit different, is we have the ability to recover from a bad layer. We can throw a page out. So that's another place where we can do this feedback loop. If we see a bad page, we can send it to a garbage can and reprint and move along our merry way there. So again, we do have some parts of the dynamic process, and but again, it's just a very early innings.
Thank you. That makes sense. So Will, you also have largely an image-based workflow. Do you have similar challenges to Len today?
Don't have the option of throwing away layers as you go. You know, it's always nice for any system if you can be able to, you know, monitor and compare and contrast, you know, as intended digital data with as printed, you know, and to be able to create a machine that is self-diagnostic. And then, you know, if you've got that ability, then being able to do other sort of layer-based Booleans as you go to, you know, modify what you're going to print in the, you know, on the printer software, as opposed to having to do it in image processing software. You know, there's benefits to being able to modify your workflow as time goes on, either on the printer or on the desktop, wherever it's appropriate. I think that was one of the things that, you know, the Dyndrite flexibility lets you kind of move things in the script from, you know, right after you slice the CAD to right before you load it into the printer.
Yeah, that makes sense. Okay, I'm going to move on to a slightly different question here before moving to a couple attendee questions. David, how do you see software development partnerships allowing you to focus on core machine technologies?
Sure. I think that's a particularly relevant question for us, because this kind of ties back to your earlier question, because we very much were running into some of the problems you were discussing earlier, with limitations around processing, just simply with large parts, and particularly complex parts. The more complex the part became, we found the processing time just to do simple operations like slicing were taking longer than the print. And that's never a good situation to be in, which is obviously where your software has transformed things quite a bit. So that's been a bottleneck, which is I guess allowed us to move forward a lot more rapidly than perhaps we would have done otherwise, if we'd had to do the work which you're doing at the moment. So yeah, from our perspective, being able to have associations like this, which enable us to focus on, I guess, the machine side of things. Not to say we're not having to do a lot of customization ourselves, because we've got a unique problem in that we're processing multiple layers of printing at the same time, which is, I guess, one of the fundamental unique things about what we do. But it does lead to very large data sets, which again just amplifies the processing issue fairly significantly when that's all being run at the same time. So yeah.
So how do you see the ability, or how do you see Aurora managing some of those large data sets in the future?
Well, we have developed some of our own internal software for this, but to some extent, and I mean, you know, I don't want to sound like too much an advertisement for you guys, but we are working very, very closely with you guys on what you're doing and how that can be utilized within our systems to process things more rapidly. So yeah, that's I guess one of the fundamental things we're doing at the moment.
Okay, thank you. So Kevin, I would like to follow up kind of with that same question with regards to Renishaw. How do you see software development partnerships fitting into the much larger Renishaw picture?
It's massive because I think one of the things that is one of the biggest challenges this industry faces is the continuous pull of two directions, one to innovate and one to standardize. And one thing's for sure, if every hardware vendor is going off and doing something quite different and innovating in different ways, there's the real risk that everything becomes so segmented that the industry as a whole can't grow. And so software partnerships are very useful because most companies operate in an agnostic fashion. There's very few companies out at the moment that are setting their flag in the sand and saying, we work with these guys or we work with these guys. I think collaboration is key because that will be the environment that allows innovation to happen, whether it be software, whether it be hardware, but that innovation is being communicated. Clearly, there's a balance there that has to be struck with how much IP is getting shared. And you know, more broadly, I see that as the challenge we face going forward, because you know, nobody wants to not innovate.
Sure. Makes sense. All right. Thanks for that. I'm going to move on to a discussion a little more about the current opportunities that we see right now, a little less of the challenges. I'm going to share my screen again briefly here. Can you see that?
Yes, we can see your screen.
Okay, thank you, Sarah.
Go ahead.
So some of the opportunities that we are considering, they've been touched on today in a couple of the talks. But first, functional part zoning. We can use the 3D distance field information for features. At least we can conceive of how to do that today. We could be feeding back results from stress analyses, similar to what Nilay said again this morning, considering stress fields, conduction areas. And this is one of the things that native GPU acceleration can enable. The performance of this solution will allow us to do things like functional part zoning. We are starting to add, and in many cases, similar to SLM talked about, multiple tools in the build zone. And in some cases, we're moving to multiple materials in the build zone, both to either increase build rate or change parameters, or again, change materials. We're looking forward towards spline toolpaths. Let's consider the machine acceleration limits in the toolpath design to both increase tool life, but also increase utilization to reduce build time. Let's make functionally derived structures such as lattices, supports, and more dynamic hatch spacing to enable more graded material properties. Also, we have opportunities to extend this tool through the Python API and other scripting environments. Again, to eliminate intermediate tools and data entry problems. And then also, as we've alluded to in several times today in this conversation, is the development of industry standards. Let's work to identify universal constraints and opportunities, and then come together to develop good rationale for the types of toolpath that we're interested in implementing to help guide some of the qualification efforts. So I would like to start with Eve again. So what toolpath challenges do you see from introducing multiple materials into the build process?
That's a good question, and that's something we've recently done with LPBF, showing that it is indeed possible to have a two-material part printed out of two metals. And the challenge here, of course, is how to prepare the data so that the laser knows what it is doing, and at the same time have a data set for the material to be deposited accordingly, right? Because for copper, you might want to have different process parameters than for steel, so to say. And that is a challenge which is difficult to solve, but the beauty of what Dyndrite provides is also within, coming back to the process control, the possibility to integrate it via the Python API, because Econity systems also share this Python API, which allows us, so to say, rather than just loading in geometrical data, being layer thickness, hedge distance, contour distance, and such, instead of loading that part in, we just load in a Python part. And that means within our system, live doing live process control, we get the chance of actually changing these geometric parameters as well. And that's the beauty of what Dyndrite brings to the table, in my humble opinion. And yeah, that helps, of course, in leveraging the whole industry and bringing new innovative products to the market.
Yeah, thank you. David, you have multiple tools also in your machine. Can you describe some of the challenges you see from adding multiple tools into the build process?
Yeah, look, I concur with the previous statements around the different materials. With one of our earlier machines, we had a range of different materials that we could introduce simultaneously, and it's really about being able to have multiple parameter sets for being able to utilize that for each different material. At the end of the day, you know, every different material is processed slightly differently, so you need a completely unique parameter set, both for the material itself and then also to do with where it's being placed in the print. Then again, for us, the other side of it is with the next generation of machines is being able to process on multiple layers simultaneously, which introduces its own set of complexities. But as I mentioned earlier, the ability to process rapidly is one of the drivers for us in being able to utilize your software, and one of the key advantages at this point in time.
Okay, thank you. So Len, I'd like to ask what your highest priorities would be for integration into the Python interface.
Well, our highest priority is really, there are a couple features we need to get from Dyndrite that are missing, but they should be easy ones. One is to be able to get a single slice at a time and get it back as in memory opposed to a file, because we don't need the whole stack at once, and sometimes we go backwards, as I mentioned, with reprinting. But the real key that I want to do, it really is where the partnership comes in, is we've got a very small team on the software side, and we're always stressed for resources like everyone. So where can we really leverage where we add the most value for what we do, and leverage the big brains at Dyndrite for what they're terrific at, which is really squeezing all these ounces of performance out of these very advanced architectures. So I think it's really get us this great slicing and these images back. There are a lot of advanced things after that to to go for. But right now, to really get this dynamic nature working.
So you're really looking more for individual slice feedback and the ability to communicate with your machine and other process analysis in quasi real time here.
Yeah, it's a very short-term goal, but yes, it's that's what's right in front of us right now.
Okay, thanks. So Kevin, when talking about some of the Renishaw machines, they've evolved from one to many tools, and toolpaths have changed to accommodate this process. What challenges has your software development team faced with keeping up with the rapid changes to the machines? And how do you see this process changing in the future?
Well, I think if you asked our software team, their probably number one complaint would be the long list of ideas that the applications engineers keep spitting out. Yeah, we're not a multi-material machine explicitly in terms of running different alloys, but we do have a number of users of our machines. Let's just talk about single laser for a moment, where they may be deliberately altering laser parameters, laser powder bed fusion machine. They may be deliberately altering laser parameters to create effectively quasi-materials. So deliberately inducing porosity, for example, for various different reasons, different mechanical properties, maybe fluid properties, things like that. If we start talking about multi-laser stuff, really the number one thing in an environment is obviously making sure that we're not getting interaction between lasers. So making sure that downwinding effects, for example, from spatter or condensate is not impacting what's going on. Clearly, most of the laser powder bed fusion machines still utilize a unidirectional gas flow in some way or another. So scanning still tends to be largely one direction, if you will. And that raises challenges in terms of thermal management. So when you start using multiple lasers and you start reducing massively layer durations, and so frequency of heat input, that puts a real strain then on understanding the thermal history of the part. So you can see a real important link up between thermomechanical modeling of the 3D printing process with multiple lasers in order to help us more rapidly develop strategies for dealing with these complex geometries, lattices, for example. And the Dyndrite software is extremely well positioned to do that because of the manner in which it's handling the data through these scripts rather than discrete geometries necessarily.
Sure. So you described that the applications engineers are coming up with ideas maybe faster than the software team can deal with them.
Mm-hmm.
How would you like to expose, or what are some of the attributes in the toolpath that you would like to expose that you think really would free up the applications engineers to developing some of those toolpaths themselves? And I think there'd be a different, I'd like to ask the same question to Will in a second, because I think this is certainly a different process to consider.
Well, I think the number one, the ultimate objective, I think that anybody in laser powder bed would probably say is would be continuously variable parameters based on the geometric history of a part, if we're still assuming 2.5D production, 3D printing, but also the material alloy that's in use. So really, at the moment, you touched on it in one of the slides you showed earlier, this idea that we're applying parameter styles according to a region, and which is typically made up of obviously many thousands of vectors. The ability to change those laser parameters, whether it be power, exposure time, point distance, whatever it may be, on the fly as a response to the geometry, as a response to the local history, would be exceedingly powerful. And at the moment, with current technology, that just isn't feasible with the amount of data that's going to be produced. So you know, that's an area of key growth, I feel, and I think that before that can really happen, we need to sort of complete the circle of pre-print simulation, print monitoring and data capture, and then analysis of that to create the loop. I think that needs to happen prior to closed loop processing, but it's going to come.
Yep, I think you're right. I think we're on track, and well, this sort of discussion I think is necessary to identify those constraints, and then we've got many partners here that are certainly pieces of the puzzle. So I'd like to get an additional perspective from Will.
I think sort of saying the same things, but from a binder jet perspective, it's nice to be able to slice in one direction and look at your lattices and how they're connected to, you know, walls, and then how do you handle the dead space inside a printer. But when you look at how those lattices are attached to a wall, slicing, you know, basically only vertically, there's some opportunities, I think, to look at that actual 3D volume, you know, in the X plane or in the Y plane or the Z plane, and looking at those slices and seeing if you're really going to be modifying different amounts of ink, or if you're able to input, you know, different powder chemistries or binder chemistries as essentially as different colors or different medias before you slice, so that you can get the right gray levels out of your printer or out of your Dyndrite software, and making sure that, you know, if you go slice some things only, you know, vertically, sometimes your lattice pattern doesn't work out exactly like you'd want it to in the middle of a part or in sharp corners. You know, bull's horns, the head might come out great, but the horns might be far too dense with the, you know, the binder levels that are created. And being able to do that kind of three-dimensional toolpath, you know, not really toolpath, but three-dimensional volumetric analysis, and looking at effectively how you shade or lattice structure the inside of a part, you know, through slicing or before slicing, that'll open doors in, you know, the binder jet side of the world for sure. But then, you know, bigger and bigger files, getting, you know, computers keep getting bigger, and hopefully the GPUs get bigger, but being able to handle the data on a finer scale, on a larger format, you know, that's another a key limitation.
Yeah. That definitely makes sense. So what are some of the critical things you're looking at when zoning a part to make those sorts of decisions?
I think if you're looking at like inside corners and outside corners, much like you have with thermal diffusion, we want to control, you know, physical migration of chemicals. And so you might want to be a little bit more careful than some of the other software manufacturers have with how you handle, you know, the inside corner of a box and how you draw your shells or how your lattices are connected to that inside corner. Can't get too far into some of it.
Yep, that makes sense.
But, you know, being able to handle those inside corners differently from outside corners, being able to handle, you know, sharp razor edges, especially with curvature. A lot of the slicing programs, they slice, but there's no, you know, volumetric dependence on how you change, you know, gray level, which was, you know, laser intensity, or, you know, ink level or whatever.
Okay, no, that makes sense. So Len, I will admit that I have very little real practical experience with your technology. Do you have a different set of constraints when you consider part zoning?
Yes, we do. I'd say there are really two things that we consider. One is the material is highly anisotropic. And so one of the things we want to do is be able to try to balance out the forces, whether it's the orientation that we build in or how much we load our powders in. But there's a second one, which we call blooming. And let me use an analogy here to try to, a highly technical one to try to explain it. Imagine you were making an egg salad sandwich. You have two pieces of bread, and you put a scoop of egg salad in between. Then you take it and you put it in a panini press. So you squish it down. That egg salad's going to squirt out the sides of the bread there. And what you're trying to do is balance out your dimensional accuracy have just enough egg salad to go up just to the edges of the bread, but have enough egg salad in there, right? Have a good sandwich. Well, our powder load is a similar constraint. If you don't have enough powder in there, you're not going to have as strong a part. But if you put too much in there, when you squeeze it, you're going to ruin your dimensional accuracy by blooming it. So if you imagine you had a hole in there and you're squeezing this thermoplastic in there, you've blown your tolerances. So one of the things that we can do with zoning, and our zones can be even on a single pixel basis, but also looking at it in a three-dimensional features is very valuable, is being able to adjust our powder loading at different pixels or different voxels in the build to try to optimize this balance of part strength versus dimensional fidelity.
That makes sense. So, Eve, could you comment on that from a multi-material perspective?
Yeah, I just wanted to jump in here because that's the same. So zoning can, of course, be applied for having different parameter sets to different geometric structures of single material parts. But of course, once you have multi-material objects in X and Y and Z, you would want different parameter sets for these different materials. And hence it is really, really important to have a zoning option which is also on a voxel basis, maybe, because if you imagine you have a gradient from X to Y, so to say, to slowly introduce one material to decrease internal stresses, then you want zones to be attached to single voxels, and yeah, that is a good opportunity.
Yeah, I'm looking forward to seeing those implemented. Very exciting. So I'm going to briefly share the screen again and move on to some of the future results that we would expect to see after we can implement some 3D feature-aware toolpaths and some of the zoning that we're talking about right now. We would expect to see less residual stress. More control over the parameters can result in less, obviously less distortion and fewer build failures. We also see this coming through a lot of the simulation software. Higher accuracy through less total part distortion, like global distortion, but also finer feature resolution through reduced power. Eventually, we'll be able to get to support free printing, as has already been demonstrated by several people in the industry today. But this requires much finer parameter control and easier DOE cycles just to do the studies to be able to then implement that on final parts. Simpler post-processing. Let's design supports that require less effort at the back end. We can design materials with better modulus and or property control through functionally grading of these materials. And then when all of this comes together, we can really expand the part families and look at new markets. So to everybody here, I'd like to ask, what is the expectation for toolpath improvements in the next 5 years, and maybe even in the next 10 years? So I'll probably let David start.
I have to get off mute first. So I guess in this industry, 5 years is a long time, and 10 years is almost a million years in the development world. But in terms of the expectations around toolpaths, I think we're going to see drivers towards some of the things you've mentioned there. So there's going to be higher resolution, there'll be multiple materials, there'll be a look towards larger and more complex products, which and people will be driving towards finer and finer controls of their respective toolpaths in different machines. And that will vary across more than just your two-dimensional structures. So people will be looking, well, our view anyway is we'll be looking to be able to control toolpaths so that the history of what's gone before will be able to affect what's occurring next. So the overall impact of that will tie in largely with what you guys are doing at this point in time. I think going back to what some of the earlier speakers said, I think one of the things that you're working on that I think is important to come out of this is a larger amount of collaboration. I think that one of the things that is, I guess, restricting the industry to some extent is, and this is, I guess, where the balance comes in, is how do you weigh up how much IP that you're giving away to against the advantages of working with a larger group of people and having a more collaborative approach to things. So yeah, I think that there's significant advantages in that approach. So yeah, that's it from my side.
That makes sense. So Will, how do you see, or what is your real expectation for the next 5 years?
Well, we can't really wait 5 years for all these fixes. I mean, these things are, a lot of them are limiting progress, you know, now. I think the finer resolution that you can control, you know, if you were to put your screen back up there, all of the items you had, all those aspects of file processing, data processing, you know, the accuracy, the support-free printing, or the, you know, supports in contact, almost in contact, internal supports within the voids of a part that, you know, unlike the cheap FDMs where you have to pull a drill out and really remove, dog warning, you know, really be able to remove all those supports, you know, physically, even if you're dissolving them out, you know, like a soluble structure on an FDM part. Being able to control all of those things at a finer data scale means that you can really impact what is part, what is support structure, what is that gray area between support structure and part. And then as all the materials become harder and stronger coming out of the machine, that accuracy turning into layer on layer smoothness and not having, you know, weird boogers hanging out the side of your FDM parts. The harder the parts, the stronger the materials get, the less tolerance you have really for inaccurate layer placement or drops that are hanging off, or, you know, features that you weren't intending to print, because they get harder and harder to remove. And all, you know, that all turns into simpler post-processing. And, you know, the residual stress, whether it's less or just controllable, it's all those things are research that are happening a lot of places now, and it's all software limited. So the faster you guys can fix these issues, you know, the faster everybody can go forward.
Yeah, that makes sense. So what would be the very first post-processing step that you would really go after?
Personally, I think the being able to manage contact point size would be a very large one. But the modulus and property control is another thing that, you know, they kind of go hand in hand. If you can control, you know, I'll stick with FDM examples for now, but if you can control how big the soluble support structure points are and how thick the soluble support structure features are, and at the same time, if you can control what the other material smoothness is at different points in the wall height, you can really control your part quality and your post-processing, the ease of getting parts out.
Yep, that makes sense.
I'm going to go back on mute because the dogs are going to go nuts.
Okay, thanks. Eve, from your perspective, what would you address first with post-processing?
Ooh, that's difficult because there is a lot to do. Well, in toolpathing, what is still bothering me is this STL format, and we apply a scan head based technology, right? And the CLI format, so to say, which we use, are straight lines, which you pointed out beforehand. So what I would love to see is basically, if you want to scan a cylinder, so to say, that you get rid of those straight lines connected, yeah, with some little delays to make sure, yeah, you get sort of tessellated cylinder object, so to say. So since the scanner itself can easily do splines, it would be great to just get rid of those straight lines for a start, so to say. And from there, I think there's still a lot to do in dynamic, yeah, changing the geometric data or toolpaths depending on the sensor data you might get in from the process and stuff like that.
Makes sense. So I'll ask a question here for Kevin. Through functionally grading parts, is this something that you have experience with as an applications engineer at Renishaw? And what do you see are the biggest constraints to this operation right now?
Yeah, it's an interesting one. So you could talk about functional grading at a couple of different levels. You could talk about it actually in terms of microstructure of the metal itself, or you can talk about it in terms of quasi materials. So anything from a lattice shape downward. In terms of functionally graded microstructures, so deliberately perhaps inducing porosity and things like that, substantially less widely used. We do have a number of customers that are doing it for very, very niche applications. One thing I would comment, looking at this slide whilst it's still in front of us and whilst we're talking about modulus and property control, each of these aspects are already handleable today. The problem is that there's an awful lot of guesswork involved, and there's an awful lot of that design work involved, and a lot of the tools that we have in our arsenal are not sufficiently flexible to go after these particular topics. So if we're just talking about the quasi materials and the modulus thing, it's shortening that development time to understand what needs to be changed and how. You know, now with something like what Dyndrite are doing, where we're using scripting engines and we can start working with geometry specifically, that opens up a lot of the playing field. It actually gives us more room to experiment, and that's a key thing, because at the moment everything we're doing is essentially numerical arrays. And it can sometimes be quite counterintuitive how that applies to an entire geometry. So yeah, I think there's that. I think there's the idea of using multiple lasers, not just to increase productivity, but to also tailor material. So utilizing chase lasers, for example, is a little term I use. This idea of controlling the thermal history of material, that could feasibly also be used to further alter moduli of materials and their behavior.
So do you have tools to start experimenting with that process today at Renishaw?
Not yet. I couldn't possibly comment on what's coming in the future, but certainly at the moment we are experimenting with the tools that are available to anybody in the industry, just by using them creatively, which, let's face it, the last 20 years of the technology is how people have been doing things. It's experimenting and kind of twisting and bending the tools to do what we want them to do. And like I say, the one thing that's exciting about what the Dyndrite toolset allows us to do is to sort of do that at will.
Yeah, thank you. Okay, so I actually here am going to take a couple of questions from Harshal.
Hey, folks. So in the interest of honestly answering a number of the questions kind of publicly that we often get, right, around what do the OEMs care about the most? What are the key new features that we're prioritizing? I mean, we at Dyndrite often basically say, well, we have this council for a reason. We specifically ask them the following question. what is the one key feature that, from a toolpathing standpoint, that we could potentially provide you that dramatically or disproportionately unlocks capability in your machine, right? And I know everyone is going to have a slightly different answer, but I figured to just go down the row and honestly publicly talk about, from a machine unlocking and capability standpoint, what is that one key killer feature? And I'll be mean by saying you can't say bigger, faster slicing. Let's just assume everything is always getting bigger and faster. What truly would dramatically unlock the potential of the machine? So I'll go kind of in the order that's currently on my Zoom, and kind of ask you to answer that question, hopefully within 30 or 40 seconds. So Eve, what's that one killer feature from a toolpathing standpoint that would unlock your machine?
Well, to put it in your words, the mic drop moment for us would be, and is what you basically already did, the ability to not load in a data file, but rather a Python API would be linked to the possibility to live change the assets of your geometric data to be printed, because that is influenced by sensor data. You might want to change what you want to print. And that can also help to deal with massive amounts of data as you get your layer in once you need it.
Thank you.
So that's basically what we showed together at last year's from Next. Mm-hmm. And I think that's a killer feature. It's not finished yet, of course, so we just showed the feasibility together with you. But I think that can enable quite a lot.
Okay. Will, same question. What's that one key killer feature that would unlock the potential of, the machines that you're already using or maybe interested in using in the future?
I think, not to jump on the faster slicing, but being able to actually manage the finer granularity, kind of that essentially three-dimensional higher resolution files without shutting down is probably the number one thing. But if you lump that into slicing, then being able to get a real three-dimensional grayscale effect to really manage, internal structure of parts would be, a game changer.
Awesome. And you already know we're working on that. Kevin, same question.
I think if you had to pin me down to one thing today, it would be the ability as an engineer to dive into any scan paths that have been generated and retrospectively start pulling them around and editing them. Even sketching profiles and asking that to be converted into a scan path style could be very powerful, could be very interesting, particularly when you get yourself into a tight corner with a niche geometry where standard style sets don't necessarily work very well, and you're very much making a choice between, a flat tire and a dead battery. Sometimes there's just no good way forward. I think that would be the number one thing. Increased ability. I think one of the things we're going to see in the future is machines with more lasers, especially laser powder bed, more lasers, higher productivity. So we're looking for systems that are intelligently working on cutting down the number of dead laser jumps, and making sure that we're maximizing process time in the machine.
So I'll double click on that for 1 second, just for the uninformed. When you're talking about scan path styles, are you talking about like the stripes and the checkerboards, or are you talking about the zigzagging patterns? Like what do you specifically mean by scan style?
Yeah, perhaps this is a sidebar. One thing we could probably do as an industry is standardizing how we refer to things a little. So things such as stripes, checkerboard, meander, we refer to as scan strategies overall for the 2D area. What we refer to at Renishaw as a scan style is individual vector types. So whether that be borders, hatching, downskin borders, downskin hatching, so on and so forth.
I see. So it's basically an amalgamation of the zoning stuff, the individual hatches themselves, and where that hatch is. Okay.
Correct. It's what I would be looking for is the ability to, from a top level, apply an overall strategy and then successively drill down and be able to modify at lower and lower levels.
Gotcha. And I might circle back, but I have more questions. Len, same question. What's that one killer feature? And I know I need to give you slice data in memory.
Okay, so I won't repeat myself. I'd say the killer feature I would take would be to either dither or feather within a certain settable distance to the edge of a contour. And this would allow us to attack that blooming problem I mentioned earlier. And then I've got some wacko way out features that we can talk about over a beer at some point.
Awesome. What's it? David, I know, again, with you guys, you know, the size is a key thing, but what would be kind of an enable killer feature for you guys beyond the speed, of course?
Yeah, look, I think the first three speakers on this actually covered all the things that I would really like in as a killer feature. Probably the only thing above and beyond that would be, I guess, very, very fine control or complete control over the ability to vary that of the scan strategies across the entire print. So being able to have the scan strategies varied and differentiated, not just within a two-dimensional structure, but across 3 dimensions would allow us a much finer degree of control. And really it's the control which leads to the end results we're after. So yeah.
Okay, so I mean, the theme that I'm getting is basically control, right? Which is ironic because on our website, all it says is power, freedom, and control all over the place. So I mean, from a control standpoint and the zoning standpoint, right? Kevin touched on, you know, the borders and the hatching patterns and, you know, where this is happening. And so did Len and Will to also a degree, right? Because you all used the words, operative words, from a border, from a downskin. Right? So beyond downskin, upskin, inskin, borders, the top of the part, the bottom of the part, right? I consider all of these kind of geometric queries. Are there other key high-level geometric queries that would help you zone or differentiate or kind of push the envelope on what the printer could do? Right? I'll ask Kevin first.
Yes. So the way that the industry is typically coming from the design for additive background, okay, the way the industry has tried to simplify things is, say, for example, a horizontal through hole, what's the maximum diameter you can do, right? Or a overhanging, totally horizontal lead, what's the longest span you can do? Which is fine, and it's definable for a given material and a given day with the wind blowing in a given direction. The problem is, everything's relative, right? So it's relative to what's gone before, what's going to come after, and basically the thermal history of the part. At the moment, I was just browsing through the Q&A and I saw a question regarding, you know, does the applications knowledge exist to actually be able to define a lot of this stuff? And frankly, I don't think it does, not well enough yet. Basically, at the moment, everything we do works with top-down styles. Which we then try and tailor to a given job. And as some of the other speakers have mentioned, to try and do this every single time for every single feature starts getting real computationally heavy. Nonetheless, before we can automate it effectively, we need to be able to manually edit this data as in depth as we possibly can. And in an efficient manner as possible. So I think you're onto something when you say they're higher level geometric things that we can use as a jump off point. My advice would be that be careful of oversimplifying it, because you might be able to define a through hole quite well, but unfortunately when you build it in something else, it may not work.
That's fair enough. I'd say, Eve, do you have any other geometric queries as well, or do you agree with Kevin? It's also okay to disagree, by the way.
No, I completely agree, because we can make up, and as you put it, control is important, but what's worth control if you have no idea what it's doing to the process? I mean, we are at Econity working a lot on in-process control, but who tells you how much laser power to take back if your part is, I don't know, 20 centigrades hotter than the layer beforehand. And that's process knowledge, and that differs for different materials, right? And that's process knowledge which is definitely not out there yet, and we will need a lot of time and a lot of engineers working on that. So maybe another feature which is important is openness. So allowing then Dyndrite, for instance, to be one of the tools for future generations of engineers to come to actually exploit what is needed to have full control over the process, because that's not there yet.
Yeah, I agree. I mean, and I think across the board, it really comes down to two options here, right? One is either the machine manufacturers themselves, like you guys on the panel, you guys invest millions and millions of dollars to go figure out every nook and cranny of a toolpathing parameter or a rasterization scheme, or you open it up a little bit to the end users and allow them to experiment and figure this out and sort of democratize it, right? I mean, I suspect this is obviously an IP minefield, but I suspect there's hopefully going to be a middle ground here that I think, you know, both sides of this fence can kind of appreciate. I'd say, Len, to kind of cap my set of questions, zoning in your process is going to be obviously very different than a powder bed fusion process.
Right.
You know, so for example, you mentioned the blooming and the filtering. What other types of geometric queries would be useful to you beyond upskin, downskin, inskin, and the border?
Yeah. So there are two I'm thinking of. One is the ability to set a camera point and do a ray cast to find a distance to intersection with the model. And if I get that, dramatically helps being able to do smart cleaning of my my objects. So I'll leave it at that. But that's one geometric query which would be interesting, but very straightforward, I think, with the platform. The other one is we have a different residual stress issue that we deal with. And again, I'll try to use an analogy here. If you were to take a box of tissue paper and you were to press down on it, the tissue paper squishes together. When you let go, it releases. And there's a spring force that is trying to push back on that compression. We have a similar thing with our fabric. When we compress it down, it wants to expand out again. So you have a spring force acting against it. And that acts as a residual stress. So we actually want to be able to measure that residual stress in areas where we're not printing, and at times put things that are similar to a support structure or a mask to try to use the thermoplastic as glue to hold those layers together to prevent the part, particularly if you have a thin wall, from ripping itself apart. So that's a very different type of geometric query I'd like to be able to do potentially, is what the residual stress is in areas where we don't print.
Let's see. So we can, I think, do a little bit of the audience Q&A at this point. Steve, do you want to handle a couple of those questions? I think some of these are very specific to either Dyndrite or, you know, might make sense for a sidebar, but do any of them stick out to you as useful to kind of the broader party? I guess.
I'm looking through them now. I think several of these are more specific to your vendor talk a little bit later.
Okay. So how about this? We will answer those questions in the vendor talk then. I'll then put it to the panelists as kind of a closing question then. What could we do to improve as Dyndrite or as end users, you know, to help provide you better information to go improve the process and tools? Right. I mean, as has been mentioned, right, the applications engineers have all kinds of ideas and things, and I'm sure that extends to all of the end users as well. I think it's rare that anyone asks the OEM, you know, what could we possibly do to make things easier for you from a product requirements gathering standpoint, or a, you know, just a helpfulness standpoint. I'd say, Kevin, do you want to go first?
Yep, absolutely. I think a good structured approach to sharing outputs is going to be key. So what I mean by that is, if we've got various users of the software, doing various different things. Let's just take laser powder bed for an example. Regardless of machine vendor, products that are printed out, maybe it's it's these standard test geometries like the NIST artifact or something like that. If we are pooling our learning in terms of metallurgy that's coming out, the metrology of the parts, how accurate they are, things like that, and understanding how the way that the Dyndrite tools are being used, is it consistent across machine platform? A couple of times already we've spoken about standardization. In order for that to happen, we have to begin getting outputs from machines that are standard for standard inputs. And at the moment, I don't see a great way for us to pull that information together.
That's fair enough. That's fair enough. I mean, to be honest, this panel was meant to be sort of the beginning of a public and private toolpathing working group, right? My assumption is that the hundreds of attendees that we have here all have interesting opinions about this. And the idea was to make a forum so that we can actually start to congeal all of this and talk about this internally and externally, in a nice way. I'd say, Eve, what about you? What could your end users possibly do better to help you develop your machines faster or improve your development process?
What our end users could improve to improve our systems? Well, pretty much similar what you do. Tell us what they need, because what we offer is a hardware platform, right? And so to us, it's important. We have different systems for different applications. So your system for dental application would look different from your system for automotive applications. And I think that also fits to the data preparation software. So you might need completely different data preparation softwares, or at least the feasibility in one data preparation software to have a tool set for, let's say, dental, and one for, let's say, automotive in terms of applicable materials when we talk about laser powder bed based processes and stuff like that. So that is important. And on the other hand, the operating system of your production is also a key challenge, right? I mean, data preparation is one part of this whole process, but quality assurance and all the tail which is coming after printing your part is also really, really important. And especially in terms of standardization, you need to make sure that the quality of your final part is what your customers want. And getting input from our customers on that and share that with you as a manufacturer or as developer for that software suite, and talking to us as manufacturer of hardware will then enable to have two solutions which might help the whole industry.
So Len, same question. Right, especially because you guys are in the process of, developing new machines, like you're birthing a new machine, right? Right. That's a fairly unique perspective, at least currently.
So the question is what we can do to open.
No, what your customers can do.
What customers do. Well, I think we're really focused towards end-use manufacturing, and one of the things for end-use manufacturing is we've got to open up the ability for customers to source and use their own material sets. I mean, it's one thing to say that you use ABS plastic, but a particular manufacturer has a particular ABS plastic they want to use, and they also many of these customers have very large purchasing departments, and the cost of these materials are very important. So we need to be able to open up these models in ways that people can use their own fabrics and their own plastics in the machine, but do it in a controlled way that, one, we can still stay in business from a financial point of view, but also that we can control the quality of what's going into it so people don't break the machines and that the parts don't get too bad and it hurts the reputation of the company. So we're working on both the business model to allow that to happen and also ways to open up the machine, and Toolpath will be a piece of that. Also, these APIs that I talk about will be another way to be able to open that up to give controlled access and be able to license it appropriately.
So we're just about done here. I'd say, Will, I'll give you 30 seconds, and David, I'll give you another 30 seconds, and we'll wrap this up. So Will, why don't you go first?
I'll answer that question slightly differently because my customer situations. But I think something that Dyndrite could do a little bit differently than you've done in the past, if possible, would be to make it easier to integrate all the other SDKs that are out there. So if you're constantly tweaking or adding or making new generations of equipment, being able to get more access to the backside of Dyndrite or however it works, to be able to pull commands from other SDKs into Dyndrite, makes it a lot easier to solve some of those problems instead of trying to come up with other applications instead of Dyndrite to be the front end of the problem, if that makes sense.
Yeah, no, and well, I appreciate that, right? And hopefully that the fact that we're getting real candid feedback publicly is hopefully also appreciated by everyone in the audience, right? Because I think it speaks to the philosophy of our company, right? So we welcome that, and I'll follow up with you about that more. I'd say, David, to close off the session.
So I guess the number one for us in terms of what we're looking for the customers to assist us is really just what you guys are asking for right now, which is direct feedback. And at the end of the day, I think that's going to be the most important thing, both for you and for us in terms of moving forward. So that's probably it for us in a nutshell.